Hi, it's Sandy with SDS Digital with a R.U.L.E module progress report. I took a break from coding the hardware to work on this HTML form that lets you add rules via Wi-Fi. I'm just beyond the prototype. All 4 blocks can be added to from this single drop-down page. In each block, there's a window where the lines, with your flow rules, can accumulate. Lines can be added, inserted, and deleted here. I'll delete this. Let's look at some of the examples of how exactly the rules are added. Rule lines are formed using the drop-downs, just like in the module. All the drop-downs can be put together in various ways to make a line. Only valid selections will show, depending on other drop-downs. The destination or condition is the first element of the line. There's quite a few to select from, as you can see. Bus and var are variables. If is a conditional statement. There are also MIDI destinations here, if you use MIDI. So we want a simple CV adder. Jack C will be the output. I'll select out to declare an output jack. Jacks A to L can be selected. I'll use Jack C, as I mentioned, which is below the A and B jacks on the panel. The arrow means put something in the destination. It could be also thought of as equals. So CVA is one source to be added to CVB. It could be a gate. So now logic symbols will show instead. Gate A or gate B to out C. The left part of the expression could be a variable. Bus 1 to 8 is a persistent variable that stays set, while var variable resets to 0 or low, depending on what it is, for the next block, a temporary variable. Bus remembers a value no matter what, which makes it useful for counters or accumulators or averagers, etc. An actual voltage value can be directly assigned to a variable or output if needed. Any number entry is done here in this box, which is a bit different from the UI in the module, as it places it in the line automatically. An integer can be used, but that would mean 1 volt, 2 volts, etc., whereas a decimal can be any voltage at all. It's all the same once it becomes a rules block line. Anyway, out C will have a total voltage of the CV at jack A plus the CV at jack B. And there's the line. This could be any math, subtract, multiply. The problem with a literal multiply, though, is quickly the numbers become larger than the 10-volt modular limit. This is why there is a special scaled multiply, denoted by a circle and with an X in the middle. The module has a symbol like that, but there's no ASCII symbol in the browser, so we're kind of stuck with this. CVB could be replaced by a decimal number, which would limit the output to less than the CVA input, if multiplied. There is also a scaled exponent that shows in the module as the exponential symbol stacked. Again, that's not an ASCII character, so I had to kind of use this. A plus B is boring, so the scaled multiply will act like a mixer. If A and B are 5 volts, then jack C will also be 5 volts. If A or B is 0 volts, jack C will output 0 volts. If A and B are 2.5 volts, then out C will be 1.25 volts, if you get the gist. This is with the scaling set as -5 to +5 volts, which is in the settings. If it was set to -10 or +10, everything would be different again. Scaling size can be set in settings. Everything would be different because if it was set from -10 to +10, then 5 volts would only be half the way up there, so 2 5-volt signals would result in 2.5 volts rather than 5 volts. So in the next line, we will deal with output F. Let's make output F quantize the voltage on the D jack. With this, out F will duplicate the CV input at jack D straight through. Quantizing it will require the int function, int. The arrow indicates a floor integer, meaning it will always choose the lower integer below the voltage on jack D. So 1.5 would equal 1, 1.9 would equal 1, 2.1 would equal 2. This could be useful this way for an octave shift at 1 volt per octave, or perhaps a selector that takes 1 volt steps. This single rule will do the job, but maybe it needs to step at 0.1 volt increments. This is how you do that. Let's do this. Use a var variable to get the value, multiply it by 10. You can't directly multiply an input, so we need to use a variable. The decimal values range is minus 9.999 to plus 9.999. We want 10, so we will use the integer value instead. It also looks a lot cleaner in the rules list. You may have noticed that I used the scaled multiply. As this number is not going directly to an output, scaling is not needed. So I'll change that to regular multiply. Now let's apply the integer transformation. It's in ones here, but will be divided by 10, so becomes steps of 0.1. This line will bring it back down to change a smooth input at jack D to a steppy output that steps 0.1 volts at a time. This almost sounds like CV semitone quantization, doesn't it? Well, yes, that can be done by simply changing the 10 to a 12, as there are 12 semitones per octave. Both lines 2 and 4 need editing. Even though the R.U.L.E module has 4 built-in customizable quantizers, it's nice to know that you don't have to use those. Keep in mind that these rules can be executed at audio rate, so out C could be mixing 2 VCOs, while these lines would be bit crushing it. Something else that could be done to the quantized signal on F is to time quantize it. To do this, just assign a time function to it. The time function isn't written directly to the output, rather it sets a parameter for the output to update every so often in seconds. The minimum time for a time function setting is 0.001, or once every 1 millisecond. I'm setting it for 100 milliseconds or 0.1 seconds. This setting is remembered. So to return to the normal 20 microsecond update rate, which is about what it is, just put time 0000. So there, that was fun. Let's go to block 2 to play with time a little bit more and show you the conditionals, which is the heart of the rules paradigm. I know this is probably a little boring, so I'll speed things up a little bit. As I mentioned, the update time of an output can be set or cleared with the time element. So either 100 milliseconds quantization on Jack I or immediate, 0. A conditional can let you switch between quantized time and normal. Let's switch it with a gate input on Jack H using an if statement. If you just put gate, GT, the interpreter assumes you mean the gate must be high. Or you can actually put high if it's easier for you to read. So if gate equals high. Now let's insert an else statement. The else statement can follow an if statement, so if the first statement is false, meaning the gate is not high, then whatever is after the else will execute instead. In this case, time on Jack I is returned to immediate. It's always a good idea to put an end if after an if statement to close it up, unless you are nesting another if statement inside. We will be adding another if statement, so without the end if, it'll only execute when the gate input is low. But then maybe that's what you might want. So here's an example of how you can use rules or conditions to get what you want in a patch. The CV voltage on Jack B will control how its own output acts. Using an equal sign with the CV inputs is not a proper way to do this, as the voltage would need to be exactly 1 volt. That's why we use the approximately equal sign instead. The approximately equal will split the voltage between this and the other approximately equal comparisons. For example, if you had 2 of them, one at 1 volt and the other at 2 volts, then the first would be true if the voltage was less than 1.5 volts but greater than 0.5 volts. The second would be true if the voltage was greater than 1.5 volts but less than 2.5 volts. This could be done using if, else, and statements, but you would only see the numbers around your target, not the actual target, which would be really confusing to look at, for more than 2 anyway. Not to mention a lot more lines would be needed to do that. I'll speed this up a bit. Here's the else statements. Now let's do weird things to the CVB signal and output it. This won't affect the result of out C that we did in the other block, but we'll send some interesting voltages from jack L. This could be a switch to patch different inputs to different destinations, or the same, like a voltage-controlled VCO switch or a voltage-controlled modulation source switch. The sky's the limit, really. I can't wait to have a look at this on the scope. This send load isn't actually finished yet, but once it is, look out. The last example is to showcase the new variable clamping operator. I'll add that in block 1. With clamping, the lower voltage must always be in a variable, as there can't be two static numbers in a declaration or in a line. The clamping symbol I created to be pretty self-explanatory. It looks like this in the module too. So variable 2 is 0. The voltage won't go below 0. Out-L used in block 2 will be clamped. Now the maximum voltage from out-L will be 3 volts. I think the multiplication in block 2 should be lower, as it will be 5 volts to 3 volts if multiplied by 10, plus the whole thing will just be clamped down to 3 volts. There, that will make 3 volts down to 1.8 volts. So there's a short tour around the module's browser-based rules editor, which for some will be quite convenient, I think. Once done, or at a certain point, you can just send it all back. This is great if you don't want to scroll the modules encoder a lot and have a lot of rules to put in. I don't know if it's any quicker though. It's an option. The Wi-Fi has been added for the future expansion modules for this module, which will all be Wi-Fi. So no wires, but this is kind of a bonus part of the addition. Those in the protocol will also be open source if you're into that sort of thing. See you in the next update. Thanks for watching.